Hello, this is the third video for the counter sequence design, and now we have to create the K-maps, which will give us the minimum sum of products Boolean expression for our counter combinational circuit design. Now you will not be given truth tables. You will have to draw your own truth tables, and you'll have to draw your own K-maps. So you need to practice this skill before you take the final exam. Now this is a very basic. As a matter of fact, these K-maps are 3 variable K-maps. I only need 2 variable K-maps, so I only need 4 squares. But on the exam, I am pretty confident that you will get a 3 variable K-map for you to design your counter. Now notice I'm putting Q1 first, because actually Q1 would be the A and Q0 would be the B. And this is a mistake that I made on my solution worksheet, and I sent a message letting you know that this is an error on my part. But you can correct that error very easily by simply changing the positions of the Q's and then redeveloping the Boolean expression that you need. Okay. So what I'm going to do now is I'm going to map these variables or these values into the K-map based on the position. A 0, 0 would be a 1. 0, 1 would be a 1. And of course I have 2 x's here. And then, since I know the position, I know it's 1, 2, 3, 4, 0, 0, 0, 1, and 1, 0, 1, 1. I can just map them directly. Now this represents the first flip-flop, which is J and K1. So that's J1 and K1. Now if you look closely, you see that there are 1s and there's x's. There's no 0s in this K-map. So that tells me that I can group all of these as a single group of 1s. So actually J is the value of 1. And likewise, the same thing seems to happen for the K. So K is the value of 1. So these values can be hardwired to VCC or high, which means that the first flip-flop will always be in the toggle mode. Now let's move on to the next set of K-maps. And now you can do all of this at once, but I'm just doing it step by step to show you the process. So now we need K-maps for the second flip-flop, which is the J0 and the K0. Remember, we're taking our inputs from the current value of the flip-flop that will drive the combinational network so that the proper values of J and K will be available for the second flip-flop. Sorry, for the next state. These are all pretty routine processes. Doesn't require a lot of thinking once you practice. So now I'm at J0 and K0. I will map these into. Now I do have some zeros here, so I won't be able to totally circle all 4 together. Now remember, x's can be converted into a 0 or a 1 as you need. So when I do the circling, I will create a 1 whenever I can use it to make my circle bigger. So here's a 1, and I could circle it alone, but I have an x to the next to it, which means that if I made that x a 1, I can create a bigger circle. Same thing here. This is 1 alone, and I can write this as a Boolean expression. However, I have an X next to it, so I'll make that X a 1 and make a bigger circle. So now I'm able to make bigger values or smaller or reduce values of output. Remember, bigger circles create smaller outputs. So it seems like this column, two columns, cancels Q0 and leaves me with Q1 as a high. And same thing over here for the K0 map. It seems like I'm canceling the 0 and I'm using the high value for Q1. What that means is that these two values here will be tied together and then connected to Q1 of the flip-flop, and that will control the transition for the second flip-flops through all 4 states. So the next video we will draw the final design, because we have just finished the next state K-map and we did the simplified loops and we did the Boolean expression. So our final job now is to make the final connections.